Have you heard of the term carbon-based life form? That's the fancy term that is used to describe pretty much every living thing. And they do say that you are what you eat. And everything that we eat, from carbohydrates to proteins, are made of carbon. How is it that carbon is found in pretty much everything? We'll answer this question in this video, so stay tuned. Assalamu alaikum everyone, this is Fahd Ansari and I'm here to help you conquer chemistry. Before we begin today's video, just a reminder that over 80% of you still haven't subscribed to my channel, so if you like the content that I'm posting, make sure that you click the subscribe button, push the bell for notifications, and without further ado, let's begin. So over here we have a methane molecule, CH4. This is the major component of natural gas, which is a fossil fuel. So basically this carbon over here also came from a carbon-based life form that existed many millions of years ago. Right, so carbon over here is bonded to 4 hydrogen atoms, and before we dive into how it is bonded to those 4 hydrogen atoms, let's look at the electronic configuration for carbon. Carbon has a proton number of 6, and so its electronic configuration is 1s2, 2s2, 2p, 2, right? And if I look at the second principal quantum shell for carbon, using this particular notation, if this looks a little alien to you, you should watch that previous video I made on this exact form of writing down the electronic configuration. Right, so over here in the 2s, I have one orbital, and remember this orbital is spherical in shape, right? And these are the 3 axes, x, y, and z, just to show that this is not a flat circle, but a sphere. Right, in the 2s subshell, I have 2 electrons with opposite spins, so that they do not repel each other so much. And the 2 electrons in the 2p subshell are located in 2 orbitals by themselves with the same spin. Remember, the 2p orbitals have a shape of a dumbbell, and we have one dumbbell along each axis. For example, this is the one along the x-axis. You'll have a similar one along the y and the z-axis. So this is the electronic configuration of carbon, but before it forms any bonds with the other hydrogen atoms in methane, what happens is these 4 orbitals in the second principal quantum shell, they're going to mix together. So you have one 2s orbital and 3 2p orbitals that are going to mix together to give you 4 new orbitals, which are going to be called sp3 orbitals, right? And what happens basically is that in each of these 4 orbitals, you're going to have one electron occupying its own orbital, right? And so these sp3 orbitals, these orbitals of this new sp3 subshell, each of them is going to be used to form a single bond with a hydrogen atom. And so if I were to zoom in on this particular carbon-hydrogen single bond, I have a carbon atom and a hydrogen atom. I have their nuclei. The carbon atom will have a hybrid orbital, which will be somewhere between the shape of an s and a p orbital. So basically what happens is you have a p orbital, one end that does not overlap becomes small, and the end that does overlap becomes larger, and so it overlaps with the orbital of the hydrogen atom, which by the way is a 1s orbital, right? And so this forms a sigma bond between the carbon atom and the hydrogen atom. And this change in shape of the carbon orbital, which is somewhere between an s orbital at the end that is overlapping, over here, and the p orbital, the end that is not overlapping over here. This mixture of shapes comes from the process known as hybridization. This whole thing over here is known as hybridization, And there are multiple types of hybridization depending on the orbitals that are mixed together to form the new orbitals, the new hybrid orbitals. In this case, this is going to be called sp3 hybridization because one s orbital and three p orbitals come together to form four new hybrid orbitals. And because each of them has one electron each, they're all going to be used to form sigma bonds like this between the carbon atom in the center and the hydrogen atoms in the corners of this methane molecule. So this is sp3 hybridization. To generalize, hybridization is the mixing of two or more atomic orbitals to produce new hybrid orbitals. So the number of new hybrid orbitals will be the same as the number of orbitals mixed. So in the previous case of sp3 hybridization, we saw that we had one orbital from the s subshell and three orbitals from the p subshell that were mixed together to give you four new orbitals in the sp3 hybridized orbitals, right? Hybrid orbitals will have the same shape and energy level as each other, right? So the same shape was obviously the dumbbell shape, but the end that does not overlap is small. The end that does overlap becomes larger, right? For better overlap between the atomic orbitals involved in a covalent bond. And the energy level will also be the same. It will be somewhere between the S and P subshell energy levels. And we already saw that in the diagram before. If you missed it, we'll do a couple more examples just to show you what I mean. And over here it says hybridization occurs in an atom before it forms bonds with other atoms, right? So once hybridization has occurred, new hybrid orbitals have been made, then it will form those sigma bonds that we saw. So hybrid orbitals can be used to either form a sigma bond with another atom if they're half full. We saw four hybrid orbitals in the sp3 hybridization process that were all half full. All of them were used to form sigma bonds. So there were four sigma bonds between the four sp3 hybrid orbitals of carbon and the s orbitals of the hydrogen atoms. And they can carry a lone pair if they are completely full. We'll see an example in the next molecule. So over here we have carbon dioxide, another carbon-based molecule that basically is removed from the human body during respiration, right? So over here we'll look at oxygen first. So oxygen, you can see, carries two lone pairs and it forms one sigma bond. So we have a total of three hybrid orbitals that we need. Two of them will be completely full and one of them will be half full. The electronic configuration of oxygen is 1s2, 2s2, 2p4, right? And if I focus on this second principal quantum shell, the valence shell over here, the 2s has two electrons with opposite spins. The 2p subshell, well, it has one electron in each of these three orbitals, and then the fourth comes into the first orbital with the opposite spin to minimize spin pair repulsion. Now, we need a total of three hybrid orbitals, right? Two of them need to be completely full and one of them needs to be half full. So now what we're going to do is we're going to pick this s orbital and these two orbitals for the p subshell, and so we're going to get three new hybrid orbitals in the sp2 hybridization that is occurring over here, because we have one orbital from the s and two from the p subshell going into this mixing process called hybridization. So two electrons from the s, two electrons from the first p orbital, and one electron from the second p orbital. So these two sp2 hybrid orbitals will carry the two lone pairs, and this will be used to form the one sigma bond that I highlighted right here. And that leaves us with this particular p orbital that does not take part in the hybridization process. It will remain a 2p orbital, This unhybridized 2p orbital is used in this particular bond over here, which is the pi bond. So the double bond is consisting of a sigma bond that involves the sp2 hybrid orbital and the pi bond that involves the unhybridized 2p orbital that was not taking part in the mixing process. So this is sp2 hybridization that I've just covered. Now finally, the last type of hybridization that is part of the AS syllabus we will look at in the case of the carbon atom. So the carbon atom over here, we've already seen its electronic configuration. It's 1s2, 2s2, 2p2. Looks something like this for the valence shell, the second principal quantum shell. Right. Now over here you can see that the carbon atom carries no lone pairs and it involves two sigma bonds. So one over here and one over here, right? So two sigma bonds and no lone pairs means that it needs two hybrid orbitals, right? So that means we will have sp hybridization because we will have one orbital from the s subshell and one orbital from the p subshell that goes into this, right? Now the question is, which of these 2p orbitals will go into the mixing process? Now remember that these two sp hybrid orbitals have one electron each because they're both forming sigma bonds, right? The carbon is forming two sigma bonds, so we would need two partially or half-filled hybrid orbitals because both of them need to be used for the sigma bonds, and there are no lone pairs, so no completely full hybrid orbitals are needed, right? So that means this 2s orbital and this empty 2p orbital will be used in the hybridization process, and these two orbitals over here that were not part of the hybridization process are going to be used to form the two pi bonds. One over here with this oxygen and one over here with this oxygen, right? So these were the three types of hybridization. This last one was sp hybridization, right? Now, if you want a quick summary of this hybridization process and how to state the hybridization of a given atom in a given molecule, is the kind of question that comes up a lot in the AS level MCQ paper, then you should watch the most recent video I uploaded, which is 1 minute short. You could go through that. This is the entire process of hybridization and the science behind it. And this is the reason why carbon atoms manage to form bonds with so many other atoms in so many different ways. And that is why carbon is found in pretty much every living thing, because of the different types of hybridization it can go through when it forms bonds with other atoms. Right, so this was all about hybridization. I hope you enjoyed this video. If you did, do leave a like, subscribe to the channel, and I'll see you in the next video.